Here we are going to do a type of hypothesis testing that will allow us to know whether two variables are independent or dependent. And the test that we'll be doing is called a chi-square test for independence. Let's first look at a typical problem in this area. A restaurant owner wants to know if there's a connection between the type of wine purchased and the type of music playing in her restaurant. She's hired you to find out. Below are the number of bottles of wine sold by type based on the type of music that was playing in the restaurant. At 5% level of significance, should we conclude that types of wine purchased and types of music playing are related? And by related, we mean are they dependent on one another? The data here is presented in the form of a contingency table. Hopefully you can recall these from some of our early probability discussions. Let's just make sure that this makes sense. For example, this 30 right here means when there was no music playing, they sold 30 bottles of French wine. And this 35 right here means when Italian music was playing, they sold 35 bottles of other types of wine. And these numbers on the outside here are totals. For example, this 99 represents the number of French bottles of wine sold, and this 84 here represents the number of bottles sold when there was no music playing. And this 243 is the total number of bottles. This is the sample size. Hopefully you recall that we've already talked about the independence or dependence of two specific events. Specifically, events A and B are independent if and only if the probability of A given B is equal to the probability of A occurring. Now, we are not specifically just looking at two events, we're looking at two variables to see if they are independent or not. So instead of just possible values of each variable and seeing if they're related, we're seeing if the entire variables are independent or dependent of one another. The reason that I put this here is not only to remind you that this is connected to what we've done in the past, but also independence goes with the equality. You remember, if you can recall, the dependence went with when these things were not equal. So when we define our hypotheses, again, there's still a pair of hypotheses we have to define. The null hypothesis, which when we're doing hypothesis testing on the mean, it has the equality. So it makes sense that the null hypothesis here with a chi-square test for independence, it would also have essentially the equality, which is independence. So let's start looking at the specifics of the chi-square test for independence. It has some similarities and some differences from the chi-square goodness of fit test. So first, in step one, the null hypothesis is that the variables are independent of one another. And the alternative hypothesis is that the variables are dependent, because remember, your hypotheses need to be complements of one another, and the complement of independence is dependence. The test statistic for step 5 is actually the same as the chi-square goodness of fit test, specifically this right here. Then some other differences from the chi-square goodness of fit test are how we compute our expected values E for our test statistic. And for a particular data point, we take the row that it is in the contingency table, its sum that is, we take the sum at the column that it's in, multiply those two numbers, and then divide by the sample size. And we get the expected value E for each of the observed values. Also, with the chi-square distribution, the number of degrees of freedom is different with the test for independence, although it's related. And in general, to get that, you take one less than the number of rows times one less than the number of columns. And similar to the chi-square goodness of fit test, the chi-square test for independence is also specifically just right-tailed. Before we go through the 6-step process for telling whether music is related to the bottles of wine that are being sold, we are going to do the computation of the test statistic in step 5 first, because with a 3x3 contingency table, the test statistic takes a while to compute. So we're going to use a whole screen just to do that computation, and then we'll look at the entire 6-step process. So recall, your observed values are your sample data. So for example, this is an O, this is an O, this is an O, this is an O, here, 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 and here. So I've already listed them. Those are my 9 observed values. Now we need to get the expected values. And remember, the expected values for each of these is the product of the row sum times the column sum divided by the sample size. So for example, let's see what we're going to put in here. That corresponds with this observed value right here. So you take the column sum, which is 75, and the row sum, which is 99, and multiply them. So we've got 75 times 99, and we have to divide by the sample size, which is 243. If you multiply and divide those, you get approximately equal to 30.6. Let's do this again for the next value. So this 30, the observed value is this one right here. To get the expected value that goes with that, we would take the column sum 84, multiply it by the row sum 99, and then divide by the sample size 243. So we've got 84 times 99 divided by 243. And that is approximately equal to 34.2. Now I've done the rest of these 7, but you would do the same sort of computation each time. And we get 34.2 for this, 9.6 for that one, 10.7, 10.7 for the one after that, 34.9, and 39.1 and 39.1. So once you have all your observed values, which were given here in the sample data, which makes up the contingency table, you need the expected values. Then we need to compute our test statistic chi-squared, which we know is the sum of the quotient of the squares of the differences of the O's and the E's with E's. By the order of operations, we first need to do the subtraction. That's why there's a subtraction column here. Then we need to do the squaring, hence the squaring of that difference column here. And we got to divide by E, which is our last column, and then we take the sum of these numbers in the last column to get our chi-squared test statistic. Let's run through this computation. So the O minus E's, we get 8.4 here, negative 4.2 here, negative 4.2 here, negative 8.6, 8.3, 0.3, 0.1, negative 4.1, and 3.9. Then if we square all these numbers, we'll get these ones here. They are approximately 70.56, 17.64, 17.64, 73.96, 68.89, 0.09, 0.01, 16.81, and 15.21. Then finally, we need to do this division here. So we need to take these squares and divide by the corresponding E's. So for this first one, we do 70.56 divided by 30.6, and we get 2.31. We continue this process, we'll get 0.52 here, 0.52 here, 7.7, 6.44, 0.01, approximately 0 here when you round to the hundredths place, 0.43, and finally 0.39. And then our test statistic, of course, is the sum of all of these in this column here, and we get 18.32. We first did the computation of the test statistic on a separate screen here because, as you can see, when there's 9 observed data values, it's a long computation. If you were computing a chi-squared test statistic for a test for independence in the professional world, you would not do this computation by hand. You would actually use a statistical package that would be able to give you this number here virtually instantaneously. Plus, our number here, 18.32, is going to have some round-off error because there was rounding done here and then new computations and rounding done over and over and over again. So to get a more precise value here, you would want to use a statistical package. And with my statistical package, I got chi-squared was 18.279. So this is not far off. However, if this test statistic was really close to the critical value that separates the rejection and the fail to reject region, then we would need to use more accuracy and probably use computer software to do it for us. We are now ready to do the 6-step process. Let's quickly read through the problem again. A restaurant owner wants to know if there's a connection between the type of wine purchased and the type of music playing in her restaurant. She's hired you to find out. Below are the number of bottles of wine sold by type based on the type of music that was playing in the restaurant. At 5% level of significance, should we conclude that the types of wine purchased and types of music playing are related? Of course, you don't see the contingency table here, but we don't need it anymore because we've already done the essential computations with it. So step 1, we define our hypotheses. The null hypothesis is that the type of music and type of wine purchased are independent of one another. And then, of course, the alternative hypothesis would be that they are dependent. And notice here, I also do not write down what the claim is. It doesn't really matter with these types of problems. Step 2 is our level of confidence. They asked us to do this at a 5% level of significance, meaning there's a 5% chance that when we make our decision, we may be committing a type 1 error. Step 3, we're doing a right-tailed chi-square test for independence. Step 4, we draw our graph. Here you can see I already have a picture of a chi-square distribution. The test is right-tailed, so we're going to shade the right-hand side, the right tail. We now need to figure out what is this value right here that separates the fail to reject region from the reject region. And in order to do that, we need to look at our chi-square distribution table, the same table that we looked at when we're doing a chi-square goodness of fit test. And we need to know alpha to read that table and the number of degrees of freedom. The number of degrees of freedom is equal to the number of rows minus 1 from the contingency table times the number of columns minus 1 also from the contingency table. And if you can recall, there were 3 types of wine and 3 types of music. So it was a 3 by 3 table. So we had 3 rows. So 3 rows minus 1 would give us 2. And there were also 3 columns. 3 columns minus 1 would give you 2. So we've got 2 times 2 is equal to 4. So the number of degrees of freedom is 4. If we now look at our chi-square distribution table with 5% alpha and 4 degrees of freedom, that gives us a critical value of 9.488. So this value right here is 9.488. So when we go on to step 5 to compute our test statistic, we want to see where it falls, whether it's in the fail to reject or the rejection region. Step 5, we've actually done the computation already on the previous screen. We got the chi-squared is equal to 18.32. And when we look down here, you can see that falls well in the rejection region. Don't forget that in step 5, not only do you compute the test statistic, but you also need to decide whether you're going to reject or fail to reject the null hypothesis. And because this landed well in the rejection region, we are going to reject the null hypothesis. In step 6, we now need to interpret our results. So we did our testing at 5% level of significance, so we're going to start with that. At 5% level of significance, again, we're rejecting the null hypothesis, so we're rejecting that the types of music and the type of wine are independent. So you can say that you're rejecting that they are independent, but rejecting that they're independent is basically saying that they are dependent. So I'm going to write it that way. So at 5% level of significance, type of music and type of wine are dependent. Type of wine purchased, that is. So this gives the restaurant owner some information to understand how her bottles of wine sell based on the type of music that she's playing. And they are, in fact, dependent at a 5% level of significance.